specific potential energy of deformation of an elastic material. Article 7.4 of the book Mechanical Systems Calculations of the Marine Facilities. Let's consider the deformation of the segment of the mechanical body under action of the main stresses. Main stresses, that is stresses, normal stresses, main action in the sides of the segment of the mechanical body, perpendicular sides of the segment of mechanical body, in which we have zero magnitudes of the shearing stresses. So the specific potential energy, specific means that the per unit of the volume, per unit of the volume, but located in the definite one point, so we consider very small volume. The specific potential energy will be equal to just one half. One half, that's just because of the Hooke's law and because of the linear increase of the deformations under the stresses and stresses under the deformations, a linear increase from zero magnitudes of the stresses and deformations. So we have the factor just one half multiplied by the brackets. In the brackets, we have a total of products of each main normal stress by the deformation in the same direction. When we substitute instead of the deformations, the strains, when you substitute the magnitudes got from the got formulas, got the previous one lesson 7.3, we had the dependencies of the deformations on the main normal stresses acting in the same direction as the deformation considered, and besides with accounted the Poisson ratio, in the brackets the total of the normal stresses in two other directions applied. Normal stresses, main stresses 2, sigma 2 and sigma 3, as we have 3 in the for the special stress strain state. And when we derive all the deformations in each of the main directions and the directions in which we have the perpendicular sides of the segment of mechanical body in the perpendicular side to the main directions, the tangential stress equal to 0. So we can find that the specific potential energy, when we substitute into the original formula, as products of the stress by the strain, stress by the strain in the main directions, stresses by the strains, one half the factor. We can find this formula as indicated here below. And after the discovering of the brackets and after the fulfillment of the required mathematical transform, we can find that the final value of specific potential energy of the deformation equals to the common factor 1 divided by 2 modulus of the elasticity of the material multiplied by the brackets. In the brackets, we have the total of squared magnitudes of the main normal stresses minus 2 multiplied by mu of the ratio of Poisson multiplied by the brackets. In the brackets is the products of the each one on the other one main normal stresses, sigma 1 by sigma 2, sigma 3 by sigma 1, sigma 2 by sigma 3, etc. So after that, the question arises, what is the part of the energy spent for the change of the volume of the segment of mechanical body, and what is the part of the energy spent for the transforming of the shape of the mechanical body? So to find the energy spent for the volume, let's consider the loading of the segment of the mechanical body by the definite arithmetic mean of the normal stresses acting on this segment of mechanical body. This is a main normal stresses, main directed perpendicular to the sides, perpendicular to the sides themselves, which are the perpendicular to each other, at which sides the shearing stress equal to 0. So we have definite one arithmetic mean, and if we substitute here, instead previously got formula here, instead of the sigma 1, sigma 2, and sigma 3, we will substitute sigma 0. we can find that after the mathematical transform that a specific potential energy spent for the change of the volume of the segment of the mechanical body under action of the normal stresses, main stress, is equal to 1 divided by 2 E. 2 is the modulus of elasticity multiplied by 3 multiplied by squared average mean of the normal stress of 3 normal stresses, 3 main normal stresses, average mean, arithmetic mean. And after that, we can substitute again instead of sigma 0. We can substitute the formula to find the sigma 0. And we will have that the specific energy spent on volume change equals to the factor we have 1 minus this formula, 1 minus u multiplied by mu, Poisson ratio, divided by 6e. 6e, it's the modulus of elasticity, multiplied by the brackets. And in the brackets, we have the main stresses acting in the sides in which tangential stress is equal to 0, and the brackets together squared. So this is energy units, specific potential energy spent for the volume change of the segment of the mechanical body and action of the main normal stresses. So what's the part spent for the change of the shape of this segment of the mechanical body? Yeah, we can do that. We can find if we will take the general formula for determination of the specific potential energy of the deformation of segment of the mechanical body under action of 3 main stresses, 3 main normal stresses, sigma 1, sigma 2, and sigma 3, and we will subtract the got magnitude of the specific energy spent for the change of the volume of the body. And after the mathematical transform, we can find the specific potential energy spent for the transformation of the shape of the segment of mechanical body. This is 1 plus mu Poisson's ratio divided by 3 by E is the modulus of the elasticity. In the brackets, we have total of squared main normal stresses minus and the products of each normal stress by other one by each other. The total potential energy of deformation is equal to the sum of energy spent for the deformation of the volume and the energy spent by deformation of the shape. And together we can find this formula consisting of these two. And of the interest is the relationship between the elastic constants of the materials. So we have 3 constants we have usually considered the modulus of the elasticity. E for stretching compression. The second, we have constant the modulus of the elasticity for shearing. We say G, and we have third constant is the Poisson's ratio. The specific potential energy calculated from shear stresses. First, we'll consider the dependence of the specific potential energy under the shearing stresses. So it's equal to the 1/2. 1/2 is usually when we consider the Cook law as the dependence of the stresses on strains increased linearly from 0, magnitudes of the stresses, the strains together. So we have just only 1/2 as probably the same factors in the square of the triangle. Is 1/2 of the product of one of the side of the triangle to the height of the triangle. 1/2 part, yeah, multiplied by tangent stress and multiplied by angular deformation, or by replacement of the angular deformation of the shear stress acting to the Hooke's law, as we consider the angular deformation as the tau shearing stress is divided by G. This is the modulus of the elasticity for the shearing of the material. The specific potential energy will be, we can substitute gamma here, and we can find that the specific potential energy of deformation equal to tau squared divided by 2 by G. So in this case, we consider this one sample. So we consider the segment of the mechanical body if only under action of the tau. So for the DEX with the not assigned magnitude, there's only assigned the tangential stresses here to the sides of the big segment. So this tangential stresses is equal due to low pairing of tangential stresses rotating to clockwise and counterclockwise. This shearing stresses, considering the balance of this segment, we can find that this stresses shearing is equal. So we have no index here, just only tau, the tangential stress. And next, let's consider the another sides in this segment, the sides of the inclination, which inclined to the side of the assigned segment, inclined by pi divided by 4, that is by 45 degrees. This is the sides of the main stresses. So we have this only for this sides. We have only the tangential stresses at these sides. So, what is the main stresses? What is the angle of the inclination? Angle of inclination is equal of tangent of 2 alpha equal to 2 divided by 0 as and thus 2 alpha. This comes from the equation of equality to 0 of the derivative of the normal stresses. Derivative of normal stresses depends on alpha angle. This derivative comes to the equality to 0, and when we substitute to the formula of tangent of the angle of the inclination for the dependence, we can find the maximal dependencies, the dependencies of maximal magnitude of the normal stresses at the angle of 2 alphas equal tangent to alpha equal to infinity. So 2 alpha equal to pi divided by 2, and alpha consequently equal pi divided by 4. This is known. The angle of inclination of the main normal stresses to the sides of the segment of mechanical body, to which we have only applied the tangential stresses. So in plane stress state, the main normal stresses and the greatest shear stresses are mutually dependent. So in this case, what is the tangential stresses? We have tangential shear stresses here. We have main normal stresses sigma 1 and sigma 3. And the tangential stress equal to, so excuse me, is we can find from this formula, but we have to find the normal stresses. They are equal to plus minus a half multiplied by square root of 4 by tangential stress assigned squared. So this equal to plus minus tau. So specific potential energy of deformation is, considering the main normal stresses, is equal, due to the formula for the plane stress state, we can find that is equal to, when we substitute with this fair form, this equation have got for the specific potential energy, and when we substitute instead of the main normal stresses, the tangential stress tau squared, we have plus minus tau squared minus etc. 2 by mu is the Poisson ratio multiplied by tau multiplied by minus tau. We can have this in one formula, mathematical transforms. And since the magnitude of specific potential energy of deformation does not depend on the choice of the coordinate system, so we have this equation of this one, the equation of the specific potential energy by the considering of the angle of deformation and action of the tangential stresses only in the place, in the absence of the normal stresses, only for the tangential stresses. And next we got that specific potential energy and the action of the normal stresses, but redefined independence on the tangential stress. So we have these two energies. This one got here the final equation, and the previous one, this equation we have two equations for the same index of the specific potential energy of the deformation. And when we equate these two parts, this one to the left one, we can find that this equation of two this and pattern this from the previous one equation of the specific potential energy, we can find that the modulus of elasticity for compression tension E and the modulus of elasticity at a shift G, second kind modulus of the elasticity, and the Poisson ratio mu are in the dependence. So the dependence is G equal to E divided by 2 in the brackets in denominator 1 plus mu. Questions and comments. 7.4.1. The potential energy of an elastic deformation and three-dimensional stress state independent on directions of the coordinate system characterizes the stress at a point that does not have deformable dimensions, which, when finding the potential energy, justifies the possibility of any choice of coordinate system. In particular, such a coordinate system, the axes of which coincide directions with the main stresses. Yes, so if we have assigned tangential stresses, we can find the deformation and the angle of deformation and action of the tangential stresses. We consider the flat stress state in the definite plane. But we have the dependence of the interdependence between the tangential stresses and the normal stresses, main normal stresses. And we can find angle of the inclination of the sides in the segment, in the mechanical body, the sides of off segment in the mechanical body, the angle of the inclination to the assigned directions of the sides, which we have only the tangential stresses. So in this inclined side, we have maximal normal stresses, that is the main normal stresses. And after the substitute the angle of inclination to the formula of definition of the main stresses, we can find the dependence of the main stresses, and we can find, on the other hand, the specific potential energy of deformation of the segment of the mechanical body and the action of the main normal stresses. But this main normal stress we can redefine by the tangential stresses. Next, we can two ways of definition of the specific potential energy. Two ways given us the same. We can equate the right sides of the formulas of two ways of definition of the specific potential energy, and after that we can just to reduce by the common factors in these two sides of the equation. The common factors is the squared tangential stress, and we can find finally the dependence of the characteristics of the material, of the elastic material. The characteristics such as the modulus of the elasticity for compression tension of the segment of the mechanical body, elastic mechanical body, and the modulus of elasticity of the second kind, that is the modulus for the sharing, for the shifting sharing of the mechanical body and the action of the tangential stresses, and the ratio of Poisson, which is dependence of the compression of the material in definite one direction, and what is dependence of the deformation in the another direction, perpendicular to the assigned compression of the definite direction. So we can find the interdependence of these elastic magnitudes due to equating of the energies of the deformation got by the action of the shearing stresses and got by the action of the main normal stresses. 7.4.2 specific potential energy of elastic deformation per unit volume equal to half the sum of the products of stresses and deformations along each of the coordinate axes associated with the directions of the main stresses. The potential energy equal to half of the sum of products, because it's equal to half of each summand in the total of the sum of the products. They equal to the half of the product because this is due to the linearity of the dependence of stresses on strains within the concept of the linear elasticity of the elastic material. The linear elasticity can begin from the zero magnitudes of as stresses, so as the strains. The dependence are linear and starting the zero magnitudes of stresses and strains. And when we find the energy as a product of stresses by strains for the inclined growth of the indexes, we can find the like the square segment of this diagram proportional for the inclined diagram as to the half. So we have 7.4.3 specific potential energy of elastic deformation per unit volume of function of the main stresses. When deformations in direction of the main stresses are redefined through these stresses. So first, to have the second part of the equation to find the dependencies of the own characteristics of the elastic material, like modulus of elasticity for compression tension and for the modulus of elasticity for the shearing and the Poisson's ratio. So first we find the potential energy considering the sharing there only for the pure sharing. Pure sharing can have, for example, when we consider the torsion of the segment of the shaft. For the torsion, we can have the pure sharing and the material of the torsion and of the shaft and the torsion. So this, and on the other hand, we can find the potential energy with not consideration of the tangential stresses only by under action of the main normal stresses on the sides which in we have no the shearing stresses. And after the equation, we next have to substitute the definition of the main normal stresses by the shearing stresses, which we added before in the articles number 7.2, 7.3, etc., 7.1. So the dependencies of the in the volumetric and in the plane stress-strain state dependencies of tangential and normal stresses. So this we need to have the equation to define the relation between the theoretical relation besides theoretical relations of interrelations of the constants of the elastic material. 7.4.4 total specific potential energy of elastic deformation and part of the energy associated with the change of the volume of deformable elastic element independent three-dimensional stress state and the part of energy spent for changing its shape. If we have the dependence of the specific potential energy on the action stresses, it would be the action stresses, the main action stresses acting on the sides of the segment of the mechanical body, in which I mean segments, the shearing stress equal to 0. So this dependence is if we can find the definite arithmetic mean of the normal stress, considering all three main normal stresses and considering the arithmetic mean, this will be only one stress, like the segment under hydrostatic pressure. This hydrostatic pressure onto the segment of the mechanical body deforms the volume and do not deform the shape of this compressed or expanded maybe mechanical body. So we can find this way the energy spent for changing the volume there only with not the change of the shape of the segment of the mechanical body. To do that, we first have to derive it's a very simple derive defining of the sigma normal stress equal to arithmetic mean of the main normal stresses. And when we substitute that into the equation of the specific potential energy of the deformation, we will find the part of the energy which having the formula of the general potential energy of deformation for the any magnitudes of the main stresses acting on the in three directions on the sides with not action of the tangential stresses on sides of segment of mechanical body. So having this equation and finding the part of this equation, not part of the magnitude got by the same equation, but only when substitute instead of this each of three equations, just the definite arithmetic mean of the normal tension got of the assigned three magnitudes of the main normal stresses. So we'll have just the part spent for the deformation of the volume. When we next we'll subtract from the general specific potential energy the part corresponded with the change of the segment mechanical body volume. The rest part remains is the part of the potential energy spent for the change of the shape of the mechanical body. Specific 7.4.5 specific potential energy of elastic deformation under pure shear, in which only the tangential stresses act in sections and the normal ones are equal to 0. Specific potential energy equal to just a half of the product of the tangential stress by the angular deformation. This we could see for the pure shear. Pure shear we can have, for example, in the case of torsion of shaft, or we can do it for the under the flat shearing force. But in the case if the external forces applied very nearly, external forces parallel applied to transverse forces applied to the beam very nearly on the planes, parallel planes located very short proximity to each other. So, but actually for the torsion, this is easy to explain. And the potential energy will be equal for the general, this potential energy will be equal for the general shaft as the product of torsion moment by the resulting torsion angle of shaft. But for the segment is equal to the product of specific per unit of the volume equal to the product of tangential stress by the angular deformation of the segment of shaft under torsion. For example, this is a pure shear. So 7.4.6. The specific potential energy of elastic deformation in a plane stress state is a function of the main stresses and the largest tangential stresses. Yeah, we first define the specific potential energy by the largest tangential stress as deformation, angular deformation of the pure shear. It is proportional to just a half of the product of the angular deformation by the tangential stress, largest, with no action of the decompression or tension of the segment of the mechanical body. On the other hand, the same specific potential energy we can define as independence of the dependence on the main stresses with no action of the shearing stress. And this we need to have the equation of two ways of definition of the specific potential energy, which differs in the mechanisms. It differs theoretically by the mechanism of the deformation, shearing or just decompression and tension, etc. So, and this is required for definition of the relation between the constants of the modulus of the elasticity for the tension compression and on the one hand, and the shearing modulus elasticity for the other hand, and the ratio, another constant, the ratio of the Poisson of the correlation of the tensions, normal tensions in other direction, and deformations in the perpendicular direction. The ratio characterized by the modulus of the by the ratio of the Poisson. To do that, for the equation, we can next, when having that definition of the specific potential energy by the normal stresses, next we can redefine these normal stresses, the main normal stresses, by the main tangential stresses in the another inclined side, so the segment of mechanical body. After a definition of the variable from the main normal stresses to the tangential stress, we can simplify the equation and find the correlation correlation among the constants of the elastic material as moduluses of the elasticity and the ratio of the Poisson. 7.4.7, the ratio of the elastic modulus of a material compression tension and undershare the shift determined by equal value of the specific potential energy of deformation for different data by the specific potential energy estimated from the highest shearing stress acting on the section inclined to the main sides at the angle of 45 degrees and by the amount of energy found by the stresses on the main sides when the tangential stresses are 0 and the normal stresses are equal to the main ones. Okay, this is just a sequence of definition sequence of the technique of definition of potential energy of deformation by two ways. One way is on the action of the tangential stresses and under the angular deformations of shear, and another one on the action of the main normal stresses with not angular informations, but with the deformations of compression and tension, linear deformations of compression. In two ways of definition of the specific potential energy deformation, we need to find the correlation among the constants of the elastic material, factors of the elasticity, two factors, and the ratio of the Poisson. Thank you.